When humans exist, we are glowing 100-watt light bulbs. A 2,000 calorie diet per day is equivalent to us glowing like a 100-watt light bulb. Now it takes 10 times the amount of energy to bring that food from the farm and to put it into a truck and put it into a refrigerator and get it into your mouth. If you just add up the energy it takes to put food on the table and eat, that's already 10 trillion watts. And then we actually have to do other things like get to work, like turn on the lights. As population grows, we're gonna need between 20 and 25 trillion watts of energy. So where are we gonna get 20 to 25 trillion watts of carbon-free energy within our lifetimes?
We can think about lots of renewables like tidal and wind and geothermal and so on, but those are not significant energy inputs.
Nuclear could be a slice of this puzzle, but even to be a slice, we would have to build 10,000 nuclear reactors over the next 50 years.
Do we want to put nuclear power plants in countries that we're already saying don't do this?
You could get to maybe piecing together a little puzzle that barely gets you to half of what you might need. But if you want to bridge that gap, we need to go to the sun. More energy from the sun hits the Earth in 1 hour than all the energy consumed by humans on our planet in an entire year. That means even if we only took a tiny fraction of what hits the Earth, we would still make more energy than we could ever dream of using as a civilization.
We love solar because we have so much of it.
The only solution that seems abundantly clear is to somehow use sunlight to power the planet.
The problem with the sun is it has this nasty habit. It goes out locally every single night. And people need energy at night too. So unless you can store sunlight, you can never use it to make primary energy for the people when they need it and where they need it.
Solar cells are one part of the solution, so solar cells provide electricity.
But unless we store it, that means we can only provide people energy between 10 a.m. and 4 p.m. on a sunny day in Arizona or in California. What happens when it rains in Boston?
There's a big chunk of energy that won't be derived from solar cells, but it might be derived from something hooked up to, sort of a creative adaptation of solar cells that can also be used to then make fuel.
What that means is taking that solar energy and converting it into a chemical fuel rather than converting it to electricity.
And that fuel, in its simplest form, is hydrogen. The sun already powers the planet through photosynthesis, and we all see that every day. The sun shines on the Earth, and plants take sunlight, water, and carbon dioxide and turn that into a fuel. It sounds pretty simple, but the machinery that they use to do that is an incredibly complex chemical machine. The question is, can you extract the essence of how it works and provide a fuel source for the planet for the long haul? And that would be a pretty cool problem to solve.
What we're trying to do is artificial photosynthesis. In essence, build a mechanical version of a leaf. Find a system that takes sunlight and water as the only two inputs, and out comes hydrogen as the fuel.
In essence, take H2O and strip the hydrogen out of H2O, which takes energy, and the energy to pull that H2 out of H2O is just sunlight.
This is an area that's really caught in between two things that people hear about on the street. Everybody's seen solar cells, everybody's seen plants, and we're trying to get into the middle ground where people really haven't gone before. Because we're not just trying to use plants and make fuel, we're trying to make fuel, but with the materials that make solar cells. This problem has many pieces to it. The first important piece is to take the sunlight directly by absorbing it and to convert its energy into electric charges.
Is that the pure compound?
And the thing that gives us that electric charge will be some really cheap implementation like solar paint. Those particles in that paste are the pigment in white paint, titania. When he drags that squeegee across that silk screening printer, some of those particles go through, and they're going to make a film onto a glass slide. The secret to get this to absorb sunlight is this dye. We take that white paint and dunk it into a solution that gets sucked onto that white material and makes it colored. And this dye on this small, tiny titania particle can take the energy from sunlight, capture that energy, and it produces electricity. And it's really cheap.
So what we want to build is an artificial photosynthesis device that has 4 components. It has sunlight, a membrane, catalysts, and water. What you want to do is split water, and so you need catalysts that facilitate splitting water.
A catalyst is something that makes something else happen faster. So let's say you're sitting there in bed and you need to go to school, and your mom comes in and tells you, get out of bed because you need to go to school. That's the catalyst in that scenario. Okay, this is something that was going to happen anyway, but just needed to be speeded up. So that's what the catalyst does.